Hi there, and thank you for watching. My name is Ben, I'm also known as Balfa, and I work as a software developer for Stack Exchange. During our company meetup in October of 2014, a bunch of us gave what we called tiny talks. Those were about 15-minute talks about pretty much any topic that we would like to talk about, and I've gotten some pretty good feedback on my talk. That's why I decided to make this recorded version of it and put it online, just in case someone else finds it interesting as well. There's some stuff in there that's specific to .NET and some C# code being used. But if you work with regular expressions on a regular basis, no pun intended, then this talk might be interesting for you anyway, even if you are not using .NET or C#. The title of my talk is Catastrophic Backtracking, when regular expressions explode. And that's a situation you don't want to be in because it means that a random user can pretty much bring your web server to a grinding halt just by inputting the wrong kind of text into a text box on your website. So that's not a nice position to be in. For the biggest part of this talk, I'll be talking about an example. And the reason for that is that the most important thing about preventing catastrophic backtracking is understanding it, knowing what's going on, what's happening behind the scenes inside the Regex engine when catastrophic backtracking occurs. And the example I am going to be using is research papers. We'll be assuming that Stack Exchange developers are now encouraged by management to write lots of academic papers, maybe in order to gain more visibility in the academic community. And being the Stack Exchange developers that we are, we of course write our research papers in Markdown. And they look like this. Now, one important thing about academic papers is that there are lots of citations in there. You quote other relevant research, you have references to other papers in there. And being the Stack Exchange developers that we are, we do not use any of the established standards of putting such references into a markdown text. Instead, we invent our own. We create these little bib blocks, bib for bibliography, and inside this bib block appear references to various other papers that are relevant in this section of the text. And all those references are, as is often the case in academic papers, just the name of the author and potentially the year that the paper was published in. So you see two examples of this here. Now, once we've written our markdown file with the text in this way, we want to in some way parse out those bib blocks to do some sort of post-processing, maybe create an index of citations or whatever we want to do with them. So we have to extract those blocks out of the markdown file. And how do we do that? Well, duh, we write a regular expression, of course. That's what we do as Stack Exchange developers. Now, we're going to create a little tool to post-process these text files. Here's the bare bones version of that. There's the regular expression up there at the top. We'll create that in a second. And then we'll just read the text file, do some line ending normalization, and then match the regular expression against the content of that markdown text file. For now, we're just going to count how many matches there are, so how many bib blocks are in the file, and we're going to measure how long it takes to find these bib blocks. Eventually, we can then actually do something with the content of these bib blocks, but for now, we just count and measure. So let's write that regular expression. Here's the text we're matching against. So the first thing we notice is that these bib blocks are separated from the other content by blank lines. So we have a double new line at the beginning and at the end of the regular expression. The next thing we see is each bib block, hence the name, starts with bib, colon, space. And then come the actual citations, of which there are one or more. One or more in regex means parentheses and a plus. And then comes the actual citation, which starts with the author name. So that's a bunch of word characters and spaces, one or more minimally matching. And in some cases, but not all, there's also the year. So that is 0 or more digits. And then comes either a comma and another citation, or we are done. We have reached the end of the bib block. So that's an alternative, and the one choice is comma and white space, either a space or a new line here. And the other possibility is that the next thing we'll be seeing is the double new line that ends the bib block. So this is a look ahead. So here's our regular expression for matching against these markdown files. And now that our tool is complete, we can run it over the text file and see what it does. And here's what it does. It says found 2 bibliography sections in 3 milliseconds. That is good because there are in fact 2 bibliography sections there, and 3 milliseconds is fast enough. Now there's just one tiny problem here. See this citation down there, Ben Collins, 2013. So yeah, Ben Collins is a great guy, and he wrote that paper, and he did all the relevant research and all the testing, writing, proofreading, and all of that. I give him that. But the thing is, the idea for writing that paper was mine. So, to be fair, he wouldn't have never written that paper if it hadn't been for my idea. So I think it's only fair that we quote this paper as Benjamin Dumke von der Ehe 2013 instead. I hope we all agree on that. And once we've made this tiny fix, we can run our tool over this markdown file again. And it's running. And running. And running. All the while our CPU looks somehow like this. And eventually our tool is actually going to finish, and it's going to say found 1 bibliography sections, yes, there is a pluralization bug in there, in 20,000 milliseconds. So not only did it only find 1 bibliography section, even though there are in fact 2, but it also took 20 seconds to do that. What's going on here? The first thing we notice when looking at this biblog is that there's a dash in my last name, which we all knew was going to be a problem at some point, and here we are. A dash is not a character that we considered when we built the author name part here of the regular expression. We did not account for dashes in author names. So my name is not a valid author name. Now this is a bug that's easily fixable, but why did it take 20 seconds for our tool to find out that this block does not in fact match this regex? In order to explain that, I'm going to highlight the parts of the text during the match attempt that are being matched against the author name part with the \w. That's the purple part here, and which parts of the text are matching against the \d. Those are the years. So this looks as expected during the first match attempt by the regular expression engine, and then the regex engine ends up here, sees the dash, and says, wait a second, I'm expecting a word character, or a space, or a digit, or a comma, or a new line. And a dash is none of these. So I cannot match like this. And what the regular expression engine does now is backtracking. It goes backwards in the string that it has so far matched and tries to find a spot where it could have matched differently, where it could have made a different decision, in the hope that by making a different decision earlier, it will later be able to continue matching and eventually finish matching this thing. Now we know that this is futile, the dash is always going to be in the way, but the regex engine is stupid. So this spot, the first spot where the regular expression engine could have made a different decision, is the 2 in Matt Gibson 2008. Because, and here's the kicker, a digit is a word character. The regex character class \w not only matches letters, and incidentally the underscore, but also digits. So while in its first attempt, the regex engine tried to match this 2 right here as a \d, which is why it's orange, it could have also decided to match this as a \w instead, make it purple. So that is what the regex engine tries now. But as I said, this is futile, the dash is still in the way. So the regex engine backtracks again and tries to make yet another decision. And the next point where it can make a different decision is now the 0 in Matt Gibson 2008, which it also tries to match as a word character, which still does not do anything good. So it also tries the other 0 and continues and still ends up at the dash, and also tries the 8 and same thing. So all of this didn't help the regex engine. It has to backtrack even further. And the next point where it can go is the 2 right here in Analia 2012. And it tries to match that as a \w instead of as a \d. Now what about Matt Gibson here? Well, we've made a different decision right here. So for the Matt Gibson part, we can try the original attempt again, which means matching all those digits as \ds in orange. But we still end up at the dash as previously, so we have to backtrack again. And now the spot where you can make a different decision is again the 2 in Matt Gibson 2008. And we try the 2, which still doesn't help. And we try the 0, which still doesn't help, and so on and so on. So you see where this is going. Once we finished with Matt Gibson here, we try the 0 in Analia 2012. Then we can try all of Matt Gibson again, and so on. Once we're done with Analia, we can backtrack to Kevin Moncho's 2009, start matching digits there as \w, and then try all of Analia and Matt Gibson again, and so on and so on. So this is going to take a while. In fact, there are 10 citations right there that have years in them. And for each of these citations, there are 5 different ways of matching, as we just saw. We can match anywhere between 0 and 4 of the digits as \d. So 10 citations with years, 5 ways for each one. That means when the regex engine tries to do all that matching, it has 5 ways to match the first citation. For each of these 5 ways, it has 5 ways to match the second one. For each of all those, it has 5 ways to match the third one, and so on and so on. All in all, that means there are 5 to the power of 10, which is almost 10 million different match attempts that the regular expression engine has to try before it can say with absolute certainty, there is no way I'll ever be able to match this string against this regular expression. And now imagine that we hadn't had 10 citations, but 11 or 12. Or imagine we hadn't had only 4 digits, but maybe 6, because we also included the month and not just the year. This number right here would escalate pretty quickly. And not just take only 20 seconds. Now, 10 million attempts in 20 seconds, that means 2 microseconds per attempt. That is fairly quick, but, you know, it escalates quickly. So now that we understand what catastrophic backtracking is, what are some ways to prevent it from occurring in the first place? And the first, I'm going to put this in scare quotes, tip I have is use a non-backtracking regex engine. There are regular expression engines that do not backtrack, and they won't fall for this. But I'm saying this is useless because you're usually going to use the regular expression engine that comes with whatever language or framework you're using. And in very many cases, including the one in the .NET runtime and the one in JavaScript in your browsers, those are backtracking. A well-known counterexample is the one in the Go language standard library. That regular expression is not backtracking, and in fact it guarantees linear time execution. But again, if you are using a language or framework where the default regex engine is backtracking, then you probably want to stay with that. So if you have any of these, and again, this includes the browser, you're stuck with what you got. So we need better tips. And here's a better tip. Be very careful when creating regular expressions with nested quantifiers. A nested quantifier, this regular expression is a simplified version of the thing we had earlier. And we see there are parentheses here with stuff on the inside, stuff on the outside. That is nesting. And a quantifier is anything where a regular expression can make a choice. And that includes the star and the plus, but also the question mark and the vertical bar. Anything where the regex engine can try different things is a quantifier. And once you're nesting these, like there's the star here on the outside, there's a star here on the inside, and a plus there. Once you nest these, be very, very careful, because those are in almost all cases the areas where catastrophic backtracking occurs. In particular, when you have these, be very, very sure that there's only one way of doing the matching and not 5, as we saw earlier. So instead of this, which caused problems, you could, for example, write this or this. Both of these are equivalent, and both of them say the first part of the regex, the \w part, should only match word characters that are not digits. And that means all word characters are going to be matched by the \w part, like real word characters, so letters, and all digits are going to be matched by the second part and by the \d part. And there's no other way to do it. So the regex engine does not have the chance to make a different decision there, and thereby preventing this catastrophic backtracking that we saw. In this particular case, we could have just gone with \w and be done with it, because we didn't actually care about where the digits were and so on. Depends on your use case. And either way, make sure there's only one way of doing that matching. Atomic grouping is a nice feature of regular expressions. It's fairly rarely used. It looks like this. You have parentheses that start with question mark greater than. And what atomic grouping tells the regular expression engine is that once it has found a match for this group inside these parentheses, and when it then later backtracks, it should not try anything else in there. It should just take the original match that it found at face value and be done with it. No backtracking in here, please. So this would have helped in our case as well, because all those different choices to be made would not have occurred. The regex engine would have just been content with what it originally found. Now, atomic grouping is not available in all regular expression engines. In particular, it's not available in JavaScript. It is available in .NET regexes, and it's available in various other regex engines, but you'll have to check if it is there in the regex engine that you're using. Atomic grouping in general is mostly a performance improvement concept in regular expressions, because even if you're not preventing a catastrophic backtracking, preventing backtracking inside certain groups can in general speed up regex matching, but it also, it modifies matching behavior. So if you use atomic grouping, be sure that you don't accidentally exclude matches that you would consider valid. If you are using .NET, then make sure that this is in your web.config. This is a fairly new option. I think it exists as of .NET 4.5. And it's called Default Regex Match Timeout. And what this does, it tells the runtime that when it's trying to match a regular expression against a string, and this match attempt takes longer than the time span specified here, 20 seconds in this case, which is already pretty long. Once a match attempt takes longer than that, the regular expression engine will stop trying and throw an exception instead. Now that means that your user gets an error page. But that is not really worse than getting no page at all. And it means that you, in your exception log, which you hopefully have, now have a an error message that tells you right there in your code is a regular expression that probably needs some love. So be sure to use that. In general, when creating regular expressions, it's always a good idea to consider the failure cases. Because in 99% of the cases, those are the problematic situations, the ones where the match attempt fails. When there is a match, when the string matches the regular expression, then that match is usually found pretty quickly. But when there is no way to match the string, the regular expression engine still has to try all those lots of combinations and has to try all of them, make sure that none of them works before it can tell you with absolute certainty there is no match here. But when you create regular expressions, most of the time you are thinking about the success case, the case where the regular expression matches, because that is usually the case that you're handling. So be sure to also spend some thoughts on the failure cases, if there is any danger in those, in particular in those cases that almost but not quite match. Like we had earlier in the case with a dash, where the dash was the only problem. Those almost but not quite matches are often the most dangerous one as far as this goes. If you're interested in some more stuff on regular expressions in general and catastrophic backtracking in particular, I can very much recommend regularexpressions.info. If you Google for catastrophic backtracking, this very page is the first hit. I think regularexpressions.info actually invented the term catastrophic backtracking, which would explain that. And there's also lots of other good stuff on there about various regular expression features, various regular expressions engines, and the differences and so on. Lots of good stuff in there. So if you're interested in regular expressions, definitely give that page a read. And having said that, this is all that there was to my talk. And again, thank you very much for watching this, and goodbye.